Good day, grade 12 learners. Welcome to today's physical science lesson. My name is Mashidu Mamboro. This lesson is brought to you by the Gauteng Department of Education in collaboration with Saibono Discovery Center. Welcome. Today we'll be revising. We'll be dealing with the knowledge area, electricity and magnetism, which is the knowledge area that you dealt with in grade 11 and is part of our exam. So I'm hoping that you will be able to do well in terms of this particular topic. And then, with no wasting of time, we'll be looking at the lesson objectives for this particular lesson to see what are the objectives that we would like to reach. That would like to reach the state Coulomb's law, which is the first thing, and then that is the first thing that we'll deal with, which is what is to state what is Coulomb's law. I know you have done it in grade 11, but it's important that you collect as many marks as possible, and more especially topics like this one under this knowledge area of electricity and magnetism. Now we are saying Coulomb's law. It says the magnitude of the electrostatic force exerted by one point charge on another charge is directly proportional to the magnitude of the charges and inversely proportional to the square of the distance between them. It is much easier when you take it from the equation itself, which is F equals to K, Q1, Q2 over R squared. So if we remove the proportionality constant there, we'll have F directly proportional to Q1, Q2 over R squared. So when we are simply saying state Coulomb's law, definitely you will refer to that equation where you will say the F there stands for the magnitude of the electrostatic force. So that is the magnitude of the electrostatic force exerted by one charge on another. So that's what you are saying. You are saying the magnitude of the electrostatic force exerted by one charge on another charge. So charge Q1 on charge Q2 is directly proportional. It's directly proportional to the magnitude of the charges. So it means as the charges increase, the electrostatic force will increase, directly proportional. But we are saying and inversely proportional to the square of the distance between them, which means now when the distance increases, the electrostatic force will decrease. Remember, we said when it comes to the magnitude of the electrostatic force, it's directly proportional to the magnitude of the charges, where Q1 and Q2, and is inversely proportional to the square of the distance between them. So always have that and remember how to state Coulomb's law. In terms of this question under electrostatics, you will see that the most important definitions that we're expecting you to remember is Coulomb's law, is electric field at a point. So as one of our first objective is for you to be able to state Coulomb's law. And we're saying always remember we're talking about the magnitude of the electrostatic force that we are saying exerted by one point charge on another point charge is directly proportional to the magnitude of the charges and inversely proportional to the square of the distance between them. Now we're going to use this equation of F equals to K, Q1, Q2 over R squared to solve problems using this equation. So we're going to use this equation to solve problems. And we're going to deal with charges that are in one dimension. We're only restricting to 3 charges here. So you will see we're talking here about Q1, Q2, and Q3, for example, but they are all in one dimension, so on a straight line like that. So we'll be able to solve them. We're not saying the straight line, they must be horizontal. It can be vertical, but as long as they are in one dimensional, we're simply saying when they are horizontal or when they are vertical. So we're talking about the one dimensional there. So we must be able to solve those, and we are only restricted to 3 charges. So we want to have a situation where we give you more than 3 charges. It will only be maximum of 3. The other one, we're going to solve problems for charges in 2 dimensions. And even here, we're referring about the right angle triangle formation, and we are still limited to 3 charges. So we're still limited to 3 charges, and we are limited to 3 charges and we can form a right angle triangle there. So that's when you are having a charge, another charge, and the third charge there, and the three are making a right angle triangle there. So you are able to see that now we are going to deal with those two scenarios. The first one being charges in one dimension with a maximum of 3 charges. The second one being charges in 2 dimensions, and then we are still restricted to only 3 charges. So we won't have more than 3 charges. So those are the first objectives that we are going to achieve for today. Now, Coulomb's law, just a background there to say, remember, it's Charles de Coulomb who investigated the force that charges or charged objects exert on each other. Hence, we call it Coulomb's law. Now, we are simply saying here now, if you are having like charges, like you are having a positive and a positive, they will repel. But if you are having unlike charges, Q1 and Q2, the other one is positive, the red one is positive, the blue one is negative there. You are able to see that unlike charges, they will attract each other, which means they will have an electrostatic force of attraction. Language is important. The force between them is electrostatic force, and it's the electrostatic force of attraction. But when we are having like charges, for example, if we are having a positive charge and another positive charge, so those are like charges, and you know what the like charges do, they will repel each other. So that is the concept that we are going to deal with, to say when we are having two charges, there's going to be electrostatic force. That force can be force of attraction or force of repulsion. So that is important, and that's what we're going to focus on. Now, we're going to look now at the electrostatic force experienced by the object. This, remember what we said? We said the electrostatic force, which is F, we said is directly proportional to the product of the charges, which means Q1 times Q2. So it's the electrostatic force is directly proportional to the product of the charges. Hence, we are saying like that. So what does that mean? It means as we increase the charges, we increase the electrostatic force. As we decrease the charges, we decrease the electrostatic force. Now, it's important, we're having a graph there. Remember, we're taking this from F equals to K, Q1, Q2 over R squared. So now, if we were to draw the graph, of F versus product of charges, the graph would look like that. You will see that the F now is on your y-axis, which is now, and you are saying Q1, Q2 is your X. So on the X, we are having Q1, Q2, and then, which means that we are having now your gradient as your R there. Your R will be remaining constant in terms of that one. So the third variable, we're keeping it constant. So we're saying you are having your force, which is on your y-axis, and the product of the charges, provided that the distance between them remains the same. So you can see the relationship between the force and the product of the charges. The main thing is that as the product of the charges increase, you can see the force is increasing. Hence, we are saying that relationship is a directly proportional relationship. So if you were to draw the graph, you will draw like that. Don't forget, provided that R remains the same, or R remains constant, which is the distance between the charges. You will understand that as the charge come closer to one another, we are simply saying that now it will affect as well the force. So hence we are saying let one R be constant, so that we can be able to look at the relationship between the force and that one. And that question is an exam question, more especially in multiple choice questions. You will get questions where we'll say, what will happen if we double the charge? What will happen if we double Q1? So you will say, if we double Q1, what will happen to the force? What you do is simply to write the formula F equals to K Q1 Q2 over R squared. You substitute the 2 there on the formula, you will be able to get K 2 Q1 Q2 over R squared. So you can see you have a 2 there, you can take it out, and then you are getting 2 K Q1 Q2 over R squared. So you can see that, oh, the force will be doubled, because you know that this is equivalent to the force. So you're able to see that if we double one charge, we'll double the force. But now, what will happen if we double both charges? The same will happen. You will go and say, okay, F equals to K. We're doubling both charges. You'll say 2Q1 multiplied by 2Q2 because we have doubled all of them. That is over R squared. And 2 times 2 is 4. So we can take out the 4 there. You will have 4 equals to, F equals to 4 KQ1 Q2 over R squared. So you can see that KQ1 over R squared is F, which means the force now will be quadrupled or will be 4 times more. So you can see that if we double both charges, the force will as well will increase by a factor of 4. So it's very much important that all the time you use the equation so that you're able to check the impact of doubling or of increasing the charges on the force. So we've demonstrated here that as we increase the magnitude of the charge, the force will as well increase. Hence, we are saying that the electrostatic force is directly proportional to the product of the charges. I hope you have that. Now, if you look now on the relationship of the electrostatic force and the square of the distance, r squared. What is the relationship? We have drawn a graph of F versus r squared. You can see on the y-axis, we are having the force there, and then on the x-axis we are having r squared, which in this case is 1 over r squared in terms of the inverse of that one. Now you are able to see that as well here we're going to have r squared and we're going to have the force. So what is the relationship? You can see the relationship that as the r increases, the force is decreasing. So can we demonstrate that? Yes, we can write the formula F equals to K Q1 Q2 over R squared. Let's say we double the distance. We double the R. If we say 2R, you are going to substitute there the 2R, which will give you K Q1 Q2 over 2R. Remember, the whole of it must be squared. So it's 2R squared. That will give you 4R squared, which means now we are having K Q1 Q2 over 4R squared. We can simply remove the 1 over 4 there, and then you will see we'll have 1 over 4 K Q1 Q2 over R squared. And then you are able to see that it means now when we increase the distance between the charges, the force will decrease by quarter, by that factor 1 over 4. So you can see that as we increase the distance between the charges, the force will decrease. But it is exponential, hence the graph is not a proportionality one. It is inversely proportional, and you can see that it's exponential because it's r squared. It doesn't mean that as you decrease or as you increase the distance, you double it, it won't decrease by 2. It will decrease by 2 squared because the distance is squared. The relationship is inversely proportional to the square of the distance between them. So when it comes to the distance, it must be squared. So it means when we double the distance, the force will decrease by 1 over 4. And then if we multiply the distance by 3, it will be 3 squared, which means that our force will decrease by a factor of 1 over 9. Please always remember that as and when you do questions, and this relationship is important as well as these graphs. I hope I've instilled that in you and you can see it's clear that you can be able to do that. Now, as we continue with electrostatics, we are saying force is a vector quantity, so the direction of the force must be indicated. So it's very much important as you are dealing with forces that these forces, they are vector quantities, so they have magnitude and direction. Remember, always when we are dealing with forces, we'll talk about the magnitude and the direction. And we are saying attracting, if the charges are unlike charges, we have attraction. Attraction is where we talked about it. Unlike charges, they attract, but like charges, they repel. And they repel in accordance with the Newton's third law. Remember Newton's third law, we're saying if an object A or an object 1 exert a force on object 2, object 2 will exert an equal but opposite force on that object. So they will be equal but in opposite in opposite direction. So the force exerted by body 1 on body 2 will be equal to the force exerted by body 2 on body 1, but in opposite direction. And then the other thing which is important is the issue of the net or the resultant force, which we are saying is a single charge can be obtained by a vector addition of all the forces acting on the charge. So always we'll ask you to calculate F net. And we are saying when you are doing F net, take direction into consideration. What does that mean? It means if F1 and F2 are moving in the same direction, definitely they will all be positive. But if they are moving in opposite direction, the other one will be positive, the other one will be negative. Hence, when you are dealing with the issue of F net, the direction is of paramount importance. I hope you will apply that as we are going to deal with questions after this. Now, this slide is there to show to you. We said we're going to restrict ourselves to maximum of 3 charges. So you can see that these charges are in 1 dimension, and we restricted ourselves to 3 charges. Sometimes we just give you 2 charges, Q1 and Q2, like that. Sometimes we'll give you 3 of them. So it's important to know that we can deal with 2 charges, we can deal with 1, 2, or 3, but a maximum of 3, not more than 3 charges. And when you say they are in 1 dimensional, I've already said it, they will be horizontal or they will be vertical. So don't be confused when you go to a paper, you are having Q1 and Q2 given like that, in that way, and then you are saying no, they must be horizontal all the time. No, we're saying 1 dimension, it means it will be either horizontal or vertical. But when you say 2 dimension, we are saying we have both horizontal and vertical, hence we are saying it's 2 dimensional. And for 2 dimensional, we're dealing with here a right angle triangle, and then we are saying we'll have charges like that, and then we can be able to solve questions based on all of this. So I hope you are ready to deal with our 1 dimension as well as our 2 dimensions, so that you are able to answer questions. Remember, when you're dealing with FNet, you will have all the forces there that you are having, and then you will be able to add the force of RT, the force because of ST as well. You're able to add them to get your FNet. So we will just do the vector sum there of those. The force of R on T plus the force of S on T. So you're able to have all that, and then you are able to get your FNet. And that's when they are 1 dimensional. But when you are dealing with this one, X, Y, Z there, you see that, okay, you're going to use a theorem of Pythagoras. So you're going to say FNet squared when you're getting the FNet there. It will be FNet squared equals to, then you have now that F of X on Y as well squared plus F of Z on Y squared. So you're able to see that you're going now to use the theorem of Pythagoras. So you will have that force there and that force there, and then you add them. And we are saying it's a vector sum. The direction is important. If the other one is negative, the other one is positive, it will have a bearing on your FNet. So you are able to do that, and then you are able to deal with your question. So you are able to know that when they're in 1 dimension, you will get the FNet like that. When they are at an angle or at a right angle triangle, 2 dimensions, we'll use the theorem of Pythagoras. I hope we're together, and then this will help you as and when we start dealing with questions. We have talked about Coulomb's law, we've talked about electrostatic force, but as well, we must talk about electric field. Electric field is important as well. So, as I indicated, here we deal with Coulomb's law, where we are focusing on the electrostatic forces, and then now we are dealing with electric field as part of this topic as well. To say, you must know how to describe an electric field. You must know how to describe an electric field as a region in space in which an electron charge experiences a force. A region of space or a region in space in which an electric charge experiences a force. What do you mean? You know, when you are playing, let's say you're playing soccer or cricket, whatever the sports that you like, you know that there is a field that you play inside there. Even when it comes to these charges, there is a field which is a region in space, like a ground in terms of that one, I'm just using it so that you can bring it home and have understanding of what we're talking about here. We're saying electric field is a region in space in which a charge experiences a force. So we are simply saying if the charges are far apart from one another, they have a long distance between them, they might not experience any force. But as you bring the charges closer, when you enter the region in space, then the charge will experience a force. So immediately when there is a force that is experienced, we say now we've entered the electric field. I know you know the magnetic field when you're dealing with your magnets there, to say if magnets are far from each other, you won't feel anything between them. But as you bring them closer, you are able now, the north and the south pole, you're able now to see that the magnetic field is increasing as you bring them closer. So it's important that you have that understanding of what is electric field. We are saying it's a region in space in which an electric charge experiences a force. So you know that that is electric field. So that is definition number 2. The first one we've defined or we've stated Coulomb law. Now the second one we're saying the definition you must know and seeing for this question is electric field. We don't have too many definitions in this section. So we're expecting you that at least these 3 you will know, which is Coulomb state, Coulomb's law. You define electric field as we're describing it. You describe electric field as a region of space in which an electric charge experiences a force, and we are saying the direction of the electric field at a point is the direction that a positive test charge will move if it is placed at that point. I would like to explain this one so that you understand this and you are able to move together. So we are simply saying if, for example, we are having a positive charge, a positively charged sphere there, when we bring a positive test charge, another positive test charge, when we bring it closer to this positive, you know positive and positive, they will repel. So definitely is that there will be repulsion, which means from a positive sign, definitely it will be away like that. The electric field will be away because our test charge is positive. So around the positive, we have the arrows, or we have the electric field that is going outward. But if we check now, if we are having a negative, when we bring a test charge that is positive, when we bring it closer there, it will be attracted. You see, which means now when you draw on this one, you will see that the arrows are towards. So you can see that negative shows attraction while positive shows repulsion. So you can see that when it's a positive charge, we will write our arrows as they are going out like that. But for a negative one, will be towards, because a positive test charge, when it comes towards a negative, it will be attracted towards it. Hence, when we draw, you will see I have a slide that is going to show you how to draw the electric field patterns. I just wanted you to understand the statement to say, have in your mind a positive test charge. To say, as I bring a positive towards a positive, what will happen? Definitely there will be repulsion. Hence, you are seeing that the positive now will be outward, as you can see it there. But as I bring the positive test charge closer to the negative, there will be attraction. Hence, towards a negative, there will be arrows that are going inside. So if you have that understanding, when you do the electric field patterns, you will understand and will move together. And we are saying you must be able to draw these electric field patterns for a single point charge and for 2-point charges. For 2-point charges, where one can be is negative, the other one is positive. Or you can have both positive or both negative. So we're expecting that you know how to draw for how many? 4 electric field patterns. That is for 1 negative, 1 positive. You can be able to draw, at least I've shown you there, for positive and for negative, and then both positive. When you have both positives, you must know how to draw when you have positive and positive. And then when you have both negative, you must do that, which is what I'm going to show to you. And then you must be able as well to define, our third definition is to define electric field at a point. Electric field at a point. And we are saying you define it as the electric field at a point is the electrostatic force experienced per unit positive charge placed at that point. So here it is your definition. It is the electrostatic force experienced per unit positive charge placed at that point. So easy, from the data sheet, you have this formula. It will always remind you what is how to define electric field at a point. So we're saying electric field at a point is electrostatic force experienced per unit positive charge placed at that point. So get this mark for definition. So either will say state Coulomb's law, define electric field at a point. When it comes to electric field, we said always have a positive test charge in your mind. To say, as I bring a positive test charge, what will be the interaction between positive and positive? We said it will be away because there will be repulsion. Between positive and negative, it will be attraction towards, hence you will draw it like that. So you have that as you draw your electric field patterns. And then we're saying electric field at a point, we said is the electrostatic force experienced per unit positive charge placed at that point. And then you're able to get all these definitions. I hope definitely the definitions are in your pocket and you are ready to collect them come your exams. Now, we are going to calculate the electric field at a point due to a number of charges using the equation to determine the contribution to the field due to each charge. So we're always looking for the contribution to the field due to each charge. So you can see, unlike when we're doing electrostatic force, because we're using both charges Q1 and Q2, and then we had to get the force of attraction or repulsion between them. Now on this one, we are looking at the contribution of each charge. So we only have one charge in our equation because we deal with them individually, these charges. Hence, we have our formula for electric field as E equals to KQ over R squared, because we want the contribution of each charge. So don't make a mistake of confusing the two formulas. The one for electric field, you can see, is the contribution of each charge. So we only need only one Q. Hence it's saying KQ over R squared, because you are dealing with the charges individually. So I hope that helps you. And as well, we're going to deal with the issue of E net, where you can be able now to add the electric field that you have calculated. Now, as promised, the electric field patterns. So these patterns, remember what I said? You must know a single point charge. We said you must know for a positive, hence you see the arrows there are outward, because we are bringing a positive test charge, hence it will repel the positive that we are bringing. But as you bring the positive charge, it will be attracted, and the arrows are going inside there. Then you are able to see that, okay, for a single point charge, we know for positive, when you bring a test charge, positive test charge, it repels. Hence, when you see positive, you see repulsion, because you are having the positive test charge in your mind. When you see negative, you see attraction, where we're attracting the positive test charge. And then when you are having 2-point charges, unlike they must attract, then you can see the arrows from the positive there. The arrows from the positive there are outward, the repulsion, towards negative, because when you bring the a positive test charge, it will be attraction. So I hope now you have the understanding to say when it's a positive and a negative, our arrows are always moved. The movement of our electric field is from positive towards negative. Then you understand it like that. If you are having a negative charge and a negative charge, two of them, now what happens? Like charges, they repel. So you can see that they won't be able to touch one another like that. They are able now to repel one another. But towards the positive, you can see that the positive, the arrows will always be going inside. But when it comes to 2-point charges that are positively charged, you can see there that the arrows are outward, because you have the positive test charge in your mind to say, as I bring the positive test charge towards these ones, they will definitely repel. And as you bring positive and positive closer to one another, they will definitely repel one another. So I hope you've understood the issue of electric field, and then we have emphasized the issue of electric field at a point, where we said at a point is the electrostatic force experienced per unit positive charge placed at that point. So you know electric field at a point as well. So electric field patterns, very much important. You will see when you do questions there will be questions that are based on the electric field patterns. Now, baseline, just to check. Remember, these topics you studied them in as early as grade 10. You were doing electrostatics there. So we just want you to remind you the basics of what you already know, to say you are not empty. In grade 11, when we went to do the topic, you did it as well in grade 10. So it's important that, hence we are saying National Senior Certificate is a 3-year course. You are doing this certificate for 3 years. It starts in grade 10, grade 11, grade 12. And if you lack the basics of grade 10, it's important, if you want to build yourself and have the foundation, it's important that we even encourage you not to throw away your grade 10 books, your grade 11 books, because you will definitely be able to go there and check where the concept started, so that at least you build on the foundation. And once you build your house on a firm foundation, we hope that you will enjoy these topics and you'll be able to do well. Now let's check our baseline. The first question there was, name at least 3 ways to charge an object. So the object, how do we charge? Whether it's positively charged or negatively charged, how do we charge them? You can think about it. Now, if I'm to remind you of ways to charge, remember by rubbing. When you're rubbing a cloth, you're rubbing a ruler in your head and all that, you always you have done that. So we are talking here, you can do that through that, which is friction. You can just use friction when you're rubbing a cloth or something against another material. And then you can do that by conduction. You can do that by induction as well. So these are some of the ways that we use and that we have done in grade 10 that tells you to say this is how we charge objects. We charge objects like that. And we can even use what is called a polarization. We can use polarization for charging of these objects. Objects can be charged like that. And then we're saying which one between the negative charge and the positive charge is transferred. Oh, a question. Which one between the negative charge and the positive charge is transferred? So this question, they are very much important. Remember, we transfer the negative charge. The negative charge is the one that is transferred. And these topics helps you as well when you are going to start and continue. Remember, you've done redox reactions in grade 11. And then there was loss of electrons and gaining of electrons. You can see everything is about the electron, which is the negative charge. Loss of electron, which when you start your redox reaction, you're going to call it oxidation, and gaining of electrons. So these signs, you must look at it holistically to say there's always somewhere where these topics, they come and meet and they talk the same language. So we know that it is the negative charge that is transferred. So the movement is the movement of the negative charge. So it is the negative charge that is transferred. Hence, I've shown you with the loss of electron and gaining of electrons. So we always talk about the electron, the negative charge. It's either is lost or gained. Then we know that we are able to move like that. Now, on 1.3 then, we're saying when the number of electrons is equal to the number of protons. So the object is said to be negatively charged, positively charged, or neutral. So that is important as well to say when the number of electrons, remember electrons are negatively charged. When the number of negative charges and the number of protons which are positively charges, when they are equal, we are saying that now the object is neutral. So when we say the object is neutral, we're saying that the electrons, the number of electrons and the number of protons are equal. So I hope you get that. And 1.4 will help us to demonstrate what we are talking about there. 1.4 is saying, what is the charge on an atom that has lost an electron? So you can see it's all about the electron, but in a paper one way, because you will still talk about electrons in terms of paper two. But the electron is an electron. It doesn't depend whether you are doing physics or you are doing chemistry. We're talking about the same electron, which is negatively charged, and the same proton that is positively charged. Now we're saying, what is the charge on an atom that has lost an electron? So you will know that if, for example, you are having sodium is number 11, in the periodic table. So you will know that sodium has 11 electrons and 11 protons. So 11 negative charges and 11 positive charges. And sodium is written as neutral. The neutral there is telling you that the number of electrons is equal to the number of protons. So you are able now to say, okay, 11 electrons, 11 protons. But if sodium loses one electron, for example, it becomes positively charged. So you got to know that when a charge, what is the charge on an atom that has lost an electron? So when you see a positive, one positive, sodium plus, you know that it means that sodium has lost one electron. But when you see, for example, magnesium 2 plus, you know that that magnesium has lost 2 electrons. So you're able to see that the 2 plus is indicating the number of electrons that have been lost. Why is that like that? Is it like that? Because we are saying the number of electrons and protons are equal. So if we lose one electron, we're going to have, for sodium, we're going to have 11 positive charges and 10 negative charges. So you can see 11 minus 10, we're remaining with positive 1. So you are able to see that when we lose one electron, we'll have sodium plus. So the question was, what is the charge on an atom that has lost an electron? So we're saying the charge is positive. It will have a positive charge. When you lose electron, you gain a positive charge. When you gain electron, you get a negative charge. So which means that now when you get a sphere that is positively charged, you know that that sphere is electron deficient, is running short of electrons. But when you have a sphere that is negatively charged, you know that it has excess of electrons. It has more electrons than protons. I hope you get that, and it helps you now to move with the equation. And what I was doing, I was explaining the answer in 1.4 to say as an atom loses an electron, it becomes positively charged. I've demonstrated to say we have equal, in a neutral atom, we have equal number of electrons and protons. But immediately we lose 1 or 2 or 3 electrons, then the atom will become positively charged. It will help you, as you hear, we are dealing mostly with positive charge, negative charge, and neutral. So our sphere that we'll be dealing with, they will be positive, negative, or neutral. So it's important for you to understand the meaning of a positive charge. You know, positive charge, it means that we have lost electrons. Negative charge, it means that we have excess of electrons. And neutral means the number of electrons and the number of protons are equal. Now, in grade 10, you have done the two kinds of charges, which is the positive charge and negative charge. You have done that positive charge is carried by protons. I just talked about it here in the nucleus. And negative charge is carried by electrons. So protons, positively charged. Electrons, negatively charged. The other thing, we're saying object can be positively charged, negatively charged, or neutral. I talked to that. They can be negative, positive, or neutral. So it's important as we give you a statement, you got to understand whether the object is positively charged, negatively charged, or neutral. You will see we'll be dealing with that aspect now. Neutral objects have equal number of positive and negative charge. I just shown you when we're explaining the pretext there to say the number of protons and the number of electrons on a neutral object, they are equal. However, immediately when you see an atom having a positive charge, you know that it has lost electrons. When you see an atom with a negative charge, you know that it has gained electrons. Now, unlike charges are attracted to each other. We talked about that when we're talking about the issue of electric field patterns. And we said like charges are repelled from each other. You have seen when we have a positive and a positive, they repel one another. When you have a negative and a negative, they repel one another. But when you have a positive and negative, you saw how the electric field patterns are drawn. And we're saying charge is neither created nor destroyed. So you cannot create, just like energy, you cannot create energy nor destroy it, but you can only be transferred. So the same with the charges, you can only be able to transfer. It means if we have a charge from this body, we can transfer it to, from this object, we can transfer it to another object, but you will never create, no. So the charges are there, we're not creating them. We're not creating them, we just transfer them. So it's the only thing that we can do to the charges is to transfer them. So it means when we are saying this object is neutral, we are talking to the issue of the charges being balanced, the positive and the negative. They are there, but they are equal. Hence, we can be able to transfer them, and they'll become unequal. Hence, when an object is positive, we know that there is now we have lost an electron. When it's negative, we know that we've gained electrons. Now, and we're saying charge is measured in coulomb. Coulomb is capital letter C, not small letter c that you use for concentration in paper 2. Coulombs is capital letter C. Don't make a mistake of writing coulomb in small letter c. And we're saying charge is quantized in units of the charge of an electron. So that is the principle of quantization of a charge. We're saying charge is quantized in units of a charge of an electron. That is, a charge of an electron is minus 1,6 times 10 to the power of minus 19. Conductors, we were saying they allow charge to move through them easily. You know, we talk about good conductors. Good conductors is those that will allow the charges to move. Insulators do not allow charge to move through them easily. And identical conducting spheres. When we're having conducting spheres that are identical, when we bring them in contact, so when we're having, for example, Q1 plus Q1 plus Q2, when you bring them in contact, what happens is that you will say the new charge will be Q1 plus Q2 over 2. I've seen equation where they brought a third charge. You can't say we're not taught about the third charge. If you bring the third charge, you will have Q1 plus Q2 plus Q3 divided by 3. Still, you'll get a new charge that we're having. And then all these, the new charge that all Q1, Q2, Q3 will have, they will now have the same sign. They will either be positive, all of them, or negative, all of them. You will see now. So it's important that you have that knowledge. In terms of our exam guideline, it refers to Q1 plus Q2 divided by 2. But if there's a question that involves 3 charges, you know that you will divide those charges by 3. Now, I talked about the principle of quantization of a charge, where we said these charges, they are quantized. We said now they have the charge of charge of an electron is equals to minus 1,6 times 10 to the power of minus 9 coulombs. So you know that is the charge of an electron. But now we have to talk to the principle of conservation of a charge. Principle of conservation of charge. Remember, immediately when a grade 12 learner sees the principle of conservation, already you know you have done so many principles of conservation by now that I know that you are singing them. The principle of conservation, you have done the principle of conservation of mechanical energy in grade 10. That is still applicable in grade 12. Where we said when you see principle of conservation, you will say the total. The total. This one is saying principle of conservation of a charge. You will say the total charge in an or of an isolated system is conserved. The total charge, so you're just bringing here total charge of an isolated system. Total charge of an isolated system is conserved. So it's important that you know the principle of conservation of a charge. And then we're saying Coulomb's law. We said the magnitude of the electrostatic force exerted by a charge Q1 on another charge Q2 is directly proportional to the magnitude of the product of the charges and inversely proportional to the square of the distance between them. So you are happy there. You must just flow and do as much as you can. Define electric field. Remember, we've defined it already to say electric field is a what? Is a region of space or region in space. So you're having a region in space or region of space where a charge experiences a force placed on that point. So when it's placed on that point, that charge will experience a force. So we're saying when you're outside of the field, you won't experience the force. But what is the electric field? We're saying it's a region of space where a charge experiences force. So the charge will experience a force. And then electric field at a point. We said electric field at a point. Here we're saying it is the force experienced, the experienced force per unit positive charge placed on that point. Don't forget per unit positive charge placed on that point. So you are armed. You are armed with all this information as you go to solve the problems. And remember what we said. We said if we are having now Q1 plus Q2, if we're having two charges that are brought together, identical charges are brought together, we said you must be able to get a new charge by adding them, dividing by 2 like that. So all this information is what we're going to utilize as we go to questions. But before we do questions, it's always important, and we're always emphasizing the use of a data sheet. You got to know this question belongs to which a topic. That is the first point. You must be able now to deal with the question in that we refer to that as you deconstruct the question, and then you check the first thing that you categorize it to say the first thing that when I get a question, I'm going to categorize it. How do you categorize the question? You are saying where is which topic are we dealing with here? So you're going to do characterization by the topic to say which topic. You said is electrostatics. Then you go to the data sheet for electrostatics so that at least when you are asked questions, you are able to respond. Remember, sometimes you are integrating topics. You heard me, I was talking about Newton's third law under these topics. So there will be those integration with other topics, but the main thing you must know that as I'm dealing with this question 7 in my paper, I will be dealing with this data sheet, which is data sheet for electrostatics. And then Coulomb's law, you are able to remind yourself there. The magnitude of the electrostatic force exerted by one charge Q1 on another charge Q2 is directly proportional to the magnitude of the product of the charges and inversely proportional to the square of the distance between them. So that formula is enough to remind you how to state Coulomb's law. And then as well, electric field at a point. We talked about it, electric field at a point. To say electric field at a point, we said is the force experienced per unit positive charge at that point, placed at that point. So you see that now already you know too. You know electric field, what we said about electric field, we said it's a region in space where a charge experiences a force. So you're able to know those 3 definitions, and this data sheet will always help you now. You know when you say calculate the electric field, you have the formula. Remember we said we are looking here for the contribution of each charge. What is the contribution of this charge? Then you are able to calculate. So we deal with them. When we talk about electric field, we're talking about each charge, the contribution of each charge, which means we only have one Q that we talked about. When we say inert, we're saying add all the contribution of these charges, their electric field. Then you are able to add and get what we call inert. And we said we're dealing with 2 dimensions and 1 dimension. 1 dimension where everything is on a straight line, can be horizontal, can be vertical. But 2 dimension, we're having a right angle triangle. I think I've emphasized that a lot. I think you know that formula you've done from grade 10 as well. You have been using that formula of potential difference equals to the work done or energy transferred per unit positive charge. I find this very useful, even as you will be doing electricity when you are defining EMF, to say the EMF is the maximum energy. It's the maximum. Remember, work done is energy transferred. So you're just putting maximum there to say this is the maximum energy per unit positive charge. That is the maximum energy supplied by the battery per unit positive charge. So you're just putting the maximum there. You can define EMF, but this is the definition of potential difference as well. So you know that the datasheet has a lot of information that is very valuable for you. Now we talked about the quantization of these charges. We said now you know that the charge of an electron is minus 1,6 times 10 to the power of minus 19 coulombs. And then obviously the charge of a proton will be positive because we said the protons are positively charged, which will be positive 1,6 times 10 to the power of minus 19. So you're able to calculate now the number of your particles there, be it a number of electrons, where you will say charge over charge of an electron. So you just take the charges that you are given, you divide by the charge of an electron, which is minus 1,6 times 10 to the power of minus 19, and then you're able to get the number of charges. Learners sometimes confuse this n with the number of moles. We're talking about here not the number of moles, but the number of particles, which can be number of electrons, number of protons that you are asked to answer here. So if you have that in mind. Don't confuse it to look like number of moles. Now we go straight into questions now. Activity for all the remaining time. We'll be dealing now with the real stuff, which is questions, because we're expecting that in the exam you will be dealing with questions. Remember, we always give you 4 options, and we are saying of those 4, 2 of them we refer to them as distractors, which are obviously incorrect answers. So it's important that you identify those, you remove them, and as you remove them, you are able to know which one now. You are increasing your chances. Remember, when you're dealing with multiple choice questions, we are simply saying that you have 25%, 1 over 4, 25% chances of getting these 2 marks. That's what we are saying when we start this question. But what are we saying? We're saying no. Now remove 2 so that you have 2 over 4. When you have 2 over 4, it means you have increased your chances to 50%. Hence, we are saying distractors must fall. Let's remove the distractors. They are there to distract us from what we want to achieve. Now, let's go to the question itself and apply this principle and this strategy of responding to multiple choice questions. This question is saying 2 oppositely charged point charges move towards each other. They move towards each other. Okay, they are opposite. So you see positive and negative. Okay, which one of the following is correct? So we're looking for the correct answer. They're saying the point charges move at constant velocity. Remember, I think I've shown you with the magnetic field to say as you bring the north and the south pole closer, you can see that as they become closer to each other, they are moving even much faster because the force is increasing. As we decrease, remember the relationship there, as we decrease the distance between them, the force increases. Remember we said the electrostatic force is inversely proportional to the square of the distance between them. So as you bring them together, you're expecting that now the object won't be moving with a constant velocity. Definitely the velocity increases because the force is more, it increases as the distance decreases. So you're able to see that, okay, we're expecting that it cannot be constant velocity, it cannot be constant acceleration. So these are definitely our disruptors. So now what is happening? And the correct answer is that now we are talking here about acceleration, which is now, it means when the object, opposite charge object, when they are moving towards each other, they increase, the acceleration is increasing. They accelerate. A good language is that they accelerate towards each other. And then because the force is highest when you have that. So the option there will be D. I hope that helps you when you deal with such kind of answers. See, let's remove the distractors and be able to get the correct answer. Now, a structured question. We are saying here 2 small identical spheres. So we're having 2 small identical spheres, which is the sphere P and sphere T. You can see them there. You see now, you cannot be confused because they are vertical. It's still the same concept. It's one dimension, and then we move. Now are placed at a distance of 0.1 meters apart. So our R is given. The force is, if they will say calculate the force, I think you will enjoy this one because you have everything. You have the Q1, Q2, you have the 2 charges, and then you have the distance between them. All you need is the constant now, and then you are able to answer the question. Now, state Coulomb's law in ways. I hope by now you are singing it. You'll be able to say the magnitude of the electrostatic force exerted by one charge, Q1, on another charge, Q2, is directly proportional to the magnitude of the product of the charges don't forget it's the product of the charges, and inversely proportional to the square of the distance between them. Remember, you can't write it in a formula, you must write it in weights. So you write the whole of it, and that's, as we've been discussing it, there it is. The magnitude of the electrostatic force exerted by one point charge on another point charge is directly proportional to the product of the magnitude of the charges and inversely proportional to the square of the distance between them. And then you get your 2 marks here. So expect 2 marks or nothing. So it's important that you know it and you state it well so that you get your 2 marks there, and then you are 2 marks richer. Now the next question, draw the resultant electric field pattern. Resultant electric patterns due to the charges on P and T. So you can see that we have a positive and a negative. You can see already that now we will have the two. Remember, we said our arrows, they will always be moving from positive towards negative. So from T to P, that's where our arrows must be moving, from T to P. And then that's how we'll draw our electric field patterns like that. There you have it. You see that you have the T that is negative, then you have the arrows that are pointing towards that. But I want to take you through the marking criteria there for this graph. To say the first mark will be for the shape. The shape. You can see it's a nice drawing. It's a nice drawing. Do that. Love what you are doing because you want 3 marks. Remember, 3 marks in physical science is 1%. 3 out of 100. Already you have 1% in the exam by understanding this electric field pattern. So it's very much important that you do this and you do it correctly. So I'm saying 1 mark is for the correct shape. 1 mark is correct direction from P to T. You can see the direction. There's our arrows. They are towards T and away from P. So that is the second mark. The third mark is that the lines must not cross. Please, we are emphasizing that the lines must not cross and must touch the spheres. So at the end of the day, the line starts from P, it ends at T. It must touch the spheres. But you see that they don't go inside the spheres and draw lines inside there where there is T and P there. You know that now you are going to do like that. They must not cross and must touch the sphere. They must touch. You can't draw the lines, then they come somewhere, they stop. Or your lines, as you draw them, they are crossing one another. So take care. This is 3 marks. This is 1% of your final exam mark if you get a question like this one. So please draw it and collect the entire 3 marks, and then we are able to move forward. Now let's go to most structured question. Structured question now. Now we are saying 2 small identical spheres, P and T. So we're having P and T. We're saying they are placed at a distance of 0.1 meters. You see the first ones that we talked about. And then as shown in the diagram below, P carries a positive charge and then T carries a negative charge. And P carries a positive 3 times 10 to the power minus 6 coulombs. T carries minus 3 times 10 to the power minus 6 coulombs. A third charge sphere S of unknown charge, so we don't know whether the charge is positive or negative, is placed at a distance of 0.1 meters. 0.1 meters from the sphere T, such that the 3 charged spheres are at vertices of a right angle triangle. So we are having our 2 dimension there. The net electrostatic force between sphere T due to the other 2 charged spheres has a magnitude of 10 newtons. So F net that T experiences is 10 newtons as indicated. So that is our resultant there, which is 10 newtons. Now, is the charge QS positive or negative? So you can see definitely that we are going to have a positive one in terms of our charge QS. And then calculate the number of electrons. Calculate the number of electrons added to or removed from the sphere S to give it a charge of QS. So we have to calculate the number of electrons. You see, it's a nice question because most of the time you are used to questions where you say calculate the electrostatic force and the likes. But now this one is saying calculate the number of electrons added to or removed from sphere S to give it to charge QS. So you're able to answer that question. And because we are dealing with that, you can now use, remember we said here we can deal with the issue of Fnet, and Fnet for a right angle triangle we use theorem of Pythagoras. So Fnet squared equals to FTP plus FTS. All of them are squared. So it's this the force here between PT and the force between TS as well, here and there. You are able to get another force. So we have the first force, which is FTP, this one, and FTS, this one. So we have to calculate all these forces, and then we have to add them. Remember, it is their square that we are dealing with now. So you see that your maths, your calculator must be handy, because you're going to have to deal with this type of equation. And then for you to deal with Fnet, already you were given that it is 10 newtons, which is our resultant force. And then you are having here the formula KQ1 Q2 over R squared for TP, and another KQ1 Q2 over R squared for TS. So you're able to do that, and then you write the formulas, the two of them as we did, and then you'll get 1 mark for your formula there. And then substitution, you have to be able to substitute. You're going to substitute Fnet, which is 10 newtons. You are going now to substitute your K, proportionality constant, which is 9 times 10 to the power of 9. You substitute now, here you have 3 times 10 to the power of minus 6 and minus 3 times 10 to the power of minus 6. So you're able to substitute there easily. And then the distance between P and T is 0,1. So it will be 0,1 squared. So this part, you are aware, you got your 1 mark. Nice. You remember is squared, because we're using the theorem of Pythagoras. Now you add it. You add it now to for TS, we're having K, which is 9 times 10 to the power of 9, and then Q1 we are having 3 times 10 to the power of minus 6, which is that one, and then that one times Q2, which is unknown. Remember, our Q2 is QS here, which is unknown, is what we must first get, and all of them squared. You see, the signs now end here, and you got now your 4 marks for the signs. That is the signs here. What is left is your maths. So important that you practice how to solve these problems. You deal with many problems as possible. And we're always encouraging you to say the calculator that we are using, ensure that you are using the same calculator, so that you don't have problems of having to learn a new calculator during exam. Then if everything done correctly, you are able to get QS, which is 4,887 times 10 to the power of minus 6. And then immediately when you get QS, you know the formula that we've given you. Q equals to NE, and then we want the number of electrons. Remember the formula that we said, number of electrons. We said number of electrons equals to charge of an electron divided by, the charge divided by charge of an electron, which we said is negative 1,6 times 10 to the power of minus 19. So that's what you're doing. You substitute the charge, you got it, it's 4,887 times 10 to the power of minus 6. You put your 1,6 times 10 to the power of minus 19 for the charge of an electron, and you are able to calculate the number of electrons, which is N equals to 3,05 times 10 to the power of 13, and then you got your 2 marks there, and then you add them to that 2, which is 6 marks. And then the only gray area that we are saying do as much practice as possible is to be able to move from here, the maths part here, to say please spend some time here dealing with the maths, so that you know how to calculate the QS, and then you are able to do that. I know that you have transposed, you took this one, all of it, you subtracted it from the 10 squared, which is 100, minus all of that, and then you are left with that one that side, and then you are able to cross multiply until you get your Q2, which in this case your QS, which is 4,887 times 10 to the power of minus 6, and then you do like that. Then you got your answer, the number of electrons as 3,05 times 10 to the power of 18. So I hope that helps you and you will know how to deal with questions like those. Now, here in activity 2.2, we are saying now P, we're having P here, is a variable point in the electric field of charged sphere A. A is a charged sphere, and R is the distance between point P and the center of the sphere A. See the diagram. So we have the diagram there that is showing us. Now, a learner determines the magnitude of the electric field. You know electric field. Said E equals to KQ over R squared. Don't forget. And we said electric at a point, E equals to F over Q. Electric field, and then we have that one, we have this one, which is F over Q for electric field at a point. So those are the two formulas when we're dealing with the electric field that we'll have in our mind. And they are saying sphere A, here we have sphere A on the graph, is then placed by next to another sphere, which is sphere B. So we have sphere A and B of different charges. So we're saying sphere A and B have different charges. Another set of results are obtained. The graph below are obtained from the results of sphere A and the graph of sphere B. You can see the graph of sphere A and the graph of sphere B. And then we're having now EA, the magnitude of the electric field at a distance of 0.04 meters from the center of charge sphere A. So the graph here is showing you the EA there, which is the magnitude of the electric field at a distance of 0.04. Remember, it's the square of the distance, hence you are having that graph there. So now, it's important for you to be able to see and look here to say, okay, we're having E equals to KQ over R squared. The graph is E. We are having KQ, but on the x-axis, you are having 1 over R squared here, which is your 1 over 0.04. So you can see that this is your Y, this is your M, this is your X. So you can see that, okay, our gradient here is KQ, because our x-axis we have 1 over R squared, and our y-axis we have E. So you're able to see that, okay, this is the graph of Y equals to MX. Our C is 0 there, there's no C. So you can see that this is a straight line. And you can see the relationship that this is a directly proportional. Now, let's go to questions now. They are saying, use the graphs to answer the following questions. State the proportionality between the magnitude of electric field at a point and 1 over R squared. So already from Coulomb's law, you know, but even the graph, it shows you it's a directly proportional relationship. Why directly proportional? You can see that there is a straight line that passes through the origin. Then you know that that is a directly proportional relationship. So that one mark you are given is there for you for your taking. And then the next question, which I want you to do, is to calculate the electric field for sphere A if the numerical value of the gradient of the graph for sphere A is 680. So I will give you just 3 minutes, but the main thing that I want you to remember is gradient. To say, how do we calculate gradient? Remember, gradient, you know, change in y over change in x. So I'm giving you a clue there, so that at least after 3 minutes, when you come back, we're doing the solution, and I hope you will have done this problem, you will have done it correctly. So see you just in about 3 minutes. Welcome back. Welcome back. I hope you enjoyed your calculation. That includes the calculation of EA using the gradient there. Now you will have what you will have done, for your changing y, you will have said, okay, your gradient is that. And remember, your gradient you are given as 680. So you know that your gradient is 680. On the y-axis, you have EA. So it's just EA, which is the final EA minus the initial, that was 0, divided by, on your x-axis, you had 1 over 0,04 squared. So you are able to just substitute minus 0 as well, so it doesn't make a difference. So you are having that. Then definitely you have to cross multiply, and then so that you can get your electric field at point A. So you're able to do the cross multiplying. You take your calculator, you have done the calculation, you had your 680 and your 1 over 4 squared, and then having done everything, yes, then you are able to get your correct answer. And then you got your final answer, if I can write it here, as your EA, which is the electric field at what? At point A, which we said is 4,425. 4,25 times 10 to the power of 5. 4,25 times 10 to the power of 25. Then you're able to get your value there. And then that's what you have done. And then you were able to get 4 marks there. So important that you have all your skills of understanding of these graphs. So graphs are important. I know you have done rates of reactions. You were talking about the graph, the gradient becoming steeper. When the gradient becomes steeper, what does it mean? When you increase the concentration, you increase the temperature, you increase those factors affecting the rate of reaction, you were saying the graph becomes steeper. So you know that the gradient is increasing there. When the graph becomes steeper, you are increasing the gradient. You were saying you are increasing the rate of reaction. It's the same kind of thinking that we are having when we are doing this. So we're saying when you learn these topics, don't learn them in isolation because they are all related. Now, here is our next question. It says, how does the magnitude of the charge on sphere B compare to the magnitude of the charge on sphere A? Right, choose from greater than, smaller than, or equals to. What is important when you are responding to this type of questions, learners, is that we started with B. You are comparing B with A. So if you say greater than, you are simply saying that the charge on sphere B is greater than. That's how you must look at it. The charge on sphere B is greater than the charge on sphere A. That's what the meaning of the word greater than mean, which is correct. It will be the charge of sphere B is greater than. Then they're saying give a reason for the answer. Remember, you're getting 1 mark for saying the charge is greater than. So what will be the reason? The reason will be that if you check, the gradient here is becoming steeper. The gradient is becoming steeper. It's moving in that direction. The gradient is coming steeper, which shows that the gradient increases, which will only mean, remember we said this graph is a graph of E equals to KQ, which we said is our gradient, and 1 over R squared, we said is our x. So in the x, we're having this, our gradient is this one. So it means now sphere B, we're having increase. Remember the relationship between E and Q. We said E equals to KQ over R squared. So you know that as we increase the magnitude of the charge, even the electric field will increase. So there is a directly proportional relationship there. So you can see that it shows that the charge here, as we increase the charge, we increase E. So you can see for sphere B, E is increasing. That must be because the magnitude of Q is increasing. Or it can be because the gradient, which is KQ, is increasing. Remember, K remains constant anyway. So you can see that, you can say that it had steeper gradient. The magnitude of the charge is increasing for sphere B. That makes the electric field as well to increase. So you're enjoying the science there. And this paper, you are going to get the entire 20 marks if you did it correct. I hope you will go and practice as many questions as possible. Now, it will have been a mistake if we don't do other questions. So I'm bringing another question so that we work. Now, look at this one. Two small identical spheres, each with mass m and charge q, are placed in a vertical cylinder. You see now, it's not always horizontal. It is still one dimension. It's just that the cylinder is vertical. The sphere remains stationary when their centers are r meters apart, as shown in the diagram below. Ignore all frictional effects. Which one of the following expression can be used to correctly calculate the distance r? Important. Now, you know our formula is F equals to K Q1 Q2 over R squared. And then if now in terms of looking for the formula now to calculate R, you will have cross multiplied there and you are going to get your, if Q1 and Q2 are equal, you will get KQ squared, definitely. So you're going to have KQ squared equals to F R squared. Our F is mg, so we can simply just say KQ squared is equals to mg R squared. And we're looking for R, so we can divide both sides by mg. You divide by mg, and then you take the square root both sides to get R. You must take the square root both sides, and then when you get the square root both sides, you're going to get R equals to square root of KQ squared over mg. You see, I didn't go and thumbsuck the answer. I've done the necessary working to get to the correct answer. KQ squared over mg. So you're able to see that your answer is A with 2 marks. So very much important that you do the calculation, and when you choose the answer, you are 100% that I'm going to get my 2 marks. I've done the correct the question correctly. Now, P is a 2 nanocoulomb point charge. So given this one is 2 nanocoulomb. It's a 0.6 centimeter. So it's important. 6 centimeter. Important. Correct SI unit. Don't forget that, because that's where we catch you now to say what is the meaning of nanocoulomb? What is the meaning of macrocoulomb? What is the meaning of picocoulomb? So always have that, because always when you're doing a calculation, you will convert to the relevant, correct SI unit. Our distance is measured in meters. Our charges are in kilo. So when you say nanocoulomb, you know we must be able to convert to the relevant coulombs that we need. Now the question was, calculate the magnitude of the electric field at X. So you know that the electric field at X can only be contributed by these 2 nanocoulomb that we're having here, which is our point P. And then with no any difficulty, when you are doing it, you will say E equals to KQ over R squared, and then you are using that 2 times 10. Don't forget that means times 10 to the power of minus 9. And then that is nanocoulomb. It was microcoulomb, you will say 10 to the power of minus 6. If it was picocoulomb, you will say 10 times 10 to the power of minus 12. So please always know how to conventions of this SI unit. And then you know your centimeters, your cents, you divide by 100. Centi, you divide by 100, hence you are getting 0.06 there squared. And then you are able to get your 5 times 10 to the power of 3 Newton per coulomb. Remember the SI unit for electric field is in Newton per coulomb, or you can just write it as 5,000 Newton per coulomb, and you are able to collect your 3 marks. I hope that helps you, and you are ready at any time when you ask such a question. Now, point charge S with a charge of minus 2 nanocoulomb, another point, is placed 4 centimeters to the right of charge P, as shown in the diagram below. So we're having these 2 nanocoulomb, we put point X. we check the contribution that was due to X of the electric field. We got 5,000 Newton per kilo. Now we are given another negative charge there. To say now we are putting where there is X, but for 4 centimeter now, we are putting another charge there. And then we're saying draw the resultant electric field patterns, important electric field patterns, practice them as many. You can see now they are horizontal. So you're able to draw, and you know how we draw them. You have a positive, and we're saying from positive, the arrows will be away. And then we're saying these lines, they must not touch, they must not cross. And then we are saying that it's always towards negative, because we thought of a test charge that it will always be attracted to the negative, and it will always be repelled by the positive. Hence our arrows are like that. So 1 mark for the shape, 1 mark for the arrows for the direction of the electric field, and 1 mark for not touching, 1 mark for that these lines, the electric field patterns, the lines must touch the sphere there. So that is the 3 marks that you got there. So you're able to say, come exam this type of questions, I will do well. At that, hey, as if that is not enough, we had a 2 nanocoulomb, we put the point X, we calculated the electric field experienced by X. We brought the negative 2 nanocoulomb, we have drawn the electric field patterns. Now we bring now the 3rd point charge, which is called T. Experiences a net electrostatic force. So it has a net electrostatic force, and it has a direction as well. So this net electric force is to the left. To the left, that is towards S. That is very much important, because if it's towards S, it means now it's being attracted to there is attraction in terms of the of that one, which will tell us what type of a charge is T. If it's going towards left, if the electrostatic force is towards there, then you know that there is attraction that side. So it must be a different charge from the negative that we're having. State Coulomb's law. By now, I think you are singing it. You state Coulomb's law, and then for your 2 marks. Now, what is the polarity of charge T? Definitely, you will know that this must be a positive charge. So you're able to say it's a positive charge. Now, 4.3. A 3rd point charge T is placed 2 centimeters to the right of S. 2 centimeters to the right, as we said, as shown in the diagram, experiencing the net. Calculate the magnitude of T. So now we want to know the charge here. What is the charge? So the question is Q. How much is the charge at T? That is what the question is all about. So you are spoiled for choice. The first option, definitely you can use the F net, which is the sum of the force here and the sum of the force there. Then you are able to calculate Q there, which is something that we have done before. And then with no wasting of time, you can simply do like that and do your substitution. So you calculated the F, the force between P and S, and you calculated the force there as T. So the first force is between S and T, which is this one. The second force is between P to T. Remember, we have these 2 charges, and then all of them is experiencing forces due to these 2 forces. So this one, force PT, and the force ST. So those 2. Don't forget, for ST, we're having 2 centimeters. You divide by 100, you get 0.02. For PT, you are having 0.04 plus 0.02, which is 0.06. So you are able now to do your substitution. You substitute nicely there, and then don't forget the force that was experienced at the F net was that one, which is 2.5 times 10 to the power of minus 4. And then you are able to do the 2, and then you write, and then at the end of the day, you want to find your QT. And then if the math is done well here, which is just now what is left is your calculator, and then you have this minus this. Definitely will subtract them, because all of them, they are common. They have QT, all of them. And then when you're done, you divide the 2.5 times 10 to the power minus 4. And if you did that one correct, you get the charge of T as 6.25 times 10 to the power of minus 9. There is another method that we can use. So you are able to get the charge at T. Now we are saying you can as well use the E, you can use the electric field. Not only that, you must rely on the electrostatic force. You can use E net as well to say, okay, if I use E net, I can as well be able now to solve the very same problem. So you do the force due to S and the force due to P, the force due to S and the force due to P. And then you are able to do that, and then with no problem, you know that, okay, I got that one is 45,000 Newton per kilo. And then when you do your E net, which is EP minus ES, then you are able to know that you are having E net like that. And then upon substitution, you get -4 times 10 to the power of 4, or you get 40,000 Newton per kilo as your electric field. And then you are able now to bring that to the electric field at a point, and then you are able to calculate the force there. The force. Remember, you have E equals to F over Q in the data sheet, and then our expectation, not much. We just want you to substitute, even if you don't have to. You don't have to make Q F the subject of the formula. You can just write the formula as it appears, and you substitute in it, and still you will get QT equals to 6,25 times 10 to the power of minus 6. Remember, this will rely on whether you chose right as positive or left as positive. So that's the two ways you can do that particular question. And always, we are always giving you a homework. This one, straightforward and nice, and we want you to enjoy it. It says A and B are two small spheres separated by 0,70 meters. Sphere A carries a charge of 1,5 times 10 to the power of minus 6 coulombs, and sphere B carries a charge of -2 times 10 to the power of minus 6 coulombs. The diagram is given there, and then you just have to answer these nice 3 questions. I hope you will enjoy doing this question as your homework, and then you will do it and check it, and you will get total. And then with that, I would like to do my summary that says, today, nice lesson, straightforward, electrostatics. I hope you are more confident now. You are looking for many questions to solve. We said electro means charges, statics means at rest. So we're saying this is the study of electric charges at rest. As I summarize the topic, we said we have charges that are given in coulombs. They are measured in coulombs. And we said we have two types of charges, which is the positive charge and the negative charge. And we said the like charges, they repel, the unlike charges, they attract. And we have indicated the elementary charge to say the electron is -1,6 times 10 to the power of minus 19 coulombs. A proton, which is positive charge, is +1,6 times 10 to the power of minus 19 coulomb. And Coulomb's law, we have stated it using that formula. We have defined both electric field and electric field at a point. So the expectation is that you will continue to revise and do as many questions as possible as you prepare for your exams. And we are saying preview of the next lesson will just in time on the 12th of June at 2:30 to 4 o'clock. We'll be doing revision of physics or paper 1. So be there and join us and come and revise and be ready for paper 1 as you'll be writing your June exams. I always like to say thank you when I close with this quote from Albert Einstein that says, anyone who has never made a mistake has never tried anything new. So let's continue to practice as many questions as possible, and then let's be ready for our exams. We are saying till we meet again. Thank you very much.